Welcome back. In this video, we're going to begin our discussion of gears and how we design gearing systems. So hopefully you've had some experience and exposure to gears before, but our particular approach in this class is going to be using our failure theories in a specific way to guide us to how we come up with our gears. So in typical with the entire design process, much of this is flexible. So you'll have certain requirements and you'll have to make choices along the way, and there are certainly wrong choices, but there are multiple possible and correct ways to doing it depending on the variables you're dealing with. So if you don't have cost metrics or things like that, it can be complicated to come up with the exact right single answer. Instead, you'll come up with a specification, and you can search for the cheapest option among those specifications. So in general, gearing design looks something like this. We're going to begin with the purpose of gears. So the purpose of a gearing system is to transmit power and to affect that power in some way. So usually there's some input power, that is speed and torque, and we want some different output speed and torque. And in order to do this, we're going to look at the aspects of the gear design and kind of do it in the process here. So the gear design process looks like this. So we're going to begin our gear design process with looking at our power requirements. So what types of power relationships do we need to see between the input and output power? That's going to give us some broad guidelines on the type of ratios we need to get. Then, in order to get the correct number of gear teeth, we're going to want to avoid interference. So we're going to find the minimum number or the maximum number of gear teeth that will avoid interference. And then once we have the gear ratios specified and we know the input speeds and torques, we can convert all of those to find out the individual forces acting on each of the gear teeth. We use our force analysis, and from our forces we'll calculate stress on the gear teeth. That stress will depend on the size of the gear teeth, including its face width, and evaluate whether the material properties can handle that using our the exact same Goodman and static failure theories that we've used before. From this, we can pull out some sizing requirements, including the sizings of the gears themselves, the materials that we want to make them out of, including their processing, any surface hardening or things like that, as well as the space needed for those gears to exist. And at any stage, this process may be iterative, so we may need to go back based on the sizes that we're getting, come back and change the sizes. And so this will interact with other systems, of course, like the bearings and the shafts which hold these gears, but we'll build on those in future lessons. So the output of this whole gear design process should be the specifications of those gears based on applying our fatigue and static failure theories. All right, let's get into it now. I'd like to briefly overview some of the types of gears. You can look at types of gears in quite a bit more detail in Chapter 13 of your textbook, but we're going to mainly focus on spur gears, and we're going to use spur gears to develop and apply all of our gear theory. And the reason is they're simplest, they are the most common. That's what you think of when you see a gear, and your mental model of a gear is generally a spur gear. But we will also look at extensively in this class helical gears, and we may look at a variation of a helical gear, which is a double helical gear, or a herringbone, which is basically two helical gears stuck together. We will also see bevel gears, although we'll discuss these less, and finally worm gears, which unfortunately we won't have a whole lot of time for, but again, you can go through your text and follow up on those if you find yourself in the need to do so. All right, so gears obviously have been around for a long time, and they've interested mechanical engineers for a long time, and so we've developed what's called gear theory, and gear theory dictates how gears interact with each other. So the fundamental principle of gear theory is that gears interact with each other optimally at what's called conjugate action. And what conjugate action means is that when two gear teeth are being pushed against each other in order to transmit force between one gear and another, that a rolling shape, which enables a rolling action, that is no sliding. Instead, this is rolling friction. It allows for the most constant speed ratio. So alternatively to conjugate action, if you can imagine the gear teeth sliding on each other or starting and stopping due to that friction, then we can assume that when one gear rotates, the motion of the other gear is not continuous or smooth. So we want that motion to be continuous and smooth transition, so we don't lose power in things like the vibrations and the heat loss. So gear teeth have a very specific design, a specific shape, which is called an involute. This shape is derived from the conjugate action presupposition. So our gear theory, conjugate action and involute, is what drives the fundamental relationships between gears, in that we can relate the speed of one gear and the speed of another gear, if they are in contact, with the ratio of their diameters, their radii, or the number of teeth. So all of these things can be used to describe them. All right. So before we can get into discussing how forces transmit from one gear tooth to another, we kind of need to get into some of the background and linguistics of gear teeth. So I'm going to present a image which comes from a Boston gear teeth catalog. You can find this whole packet on Blackboard as well. All right, so there's several important phrases that we use when we're talking and referring to gears. To begin with, when we say one gear is interacting with another gear, we say that the pinion gear, which is the smaller of the gears, drives a gear. So the pinion is generally referred to as the smaller one, and the gear is the larger. Second, a gear tooth profile is that involute shape. It is that involute shape riding on another involute shape which gives us our conjugate action, a smooth transition from one to another. And that action happens along a particular line. So this line is defined by a pressure angle from the tangent of those two gears. So if you make a line between the center to center of the gears, a line that is perpendicular to that will have a pressure angle defining how those teeth interact. So there's a particular angle here, and that angle, of course, is going to determine how much of the force goes into turning the gear and how much of the force from that torque goes into pushing the gears into each other. And those forces of pushing into each other are then, of course, resisted by the shaft and the bearings which support them. Next, we'll use the phrase pitch circle quite a bit. So a pitch circle is defined as the distance of a gear tooth and the space of one gear tooth. So the pitch circle looks like a gear tooth plus the gap before the next gear tooth. So the pitch circle, I'll call it the PC, is the gap between those two. So the pitch circle and the width of the tooth can combine to tell you what the gap is. So the pitch circle minus the width of the tooth is what's called backlash. And it's the space between that allows a tooth to come into that space and then leave that space. And you can have gears that are called anti-backlash gears which reduce the amount of noise and vibration between those, but they require higher precisions in mounting. So the more backlash you have, the more flexibility you have in allowing those gears to wiggle around a little bit. If you have a very low tolerance for backlash, then you're going to need a lot higher specifications on your bearings and shafts. So the design constraints that are going to be most interesting to us are the number of teeth on either the pinion or the gear, the center-to-center distance, and finally the pitch. And usually when I say pitch, I mean diametral pitch. Or alternatively, if we're going to be using a metric gears, we're going to call this the module. The pitch and the module are not equal to each other, but they reference the same thing. They mean how many gear teeth are on the gear with respect to the diameter of that gear. And finally, the last part of gear teeth that we'll be specifying is what's called the face width. The face width is how much gear teeth there is to rub against another gear teeth. So in this image, the width goes in and out of the page. All right, now let's talk about pitch and module a little bit more. So the diametrical pitch, let's say dP, is equal to the number of teeth on the gear divided by the pitch diameter. So the pitch diameter is the diameter of the circle that is imposed on that gear, made up of the points of where one gear tooth connects to another gear tooth. So it is not the outside diameter of the gear, nor is it the inside diameter. In fact, it tends to be about 40% of the gear tooth's length down from the outside diameter. So this diametrical pitch, or diametral pitch, the diametral pitch is the imperial method of specifying gears. So American gears generally are specified with diametral pitch, but for the most part, any gear catalog you look at, you can easily swap between the two. And it is in measurements of teeth per inch. Pitch diameter is the diameter of the pitch circle. The module is usually used a lowercase m, and the module is, in a way, the inverse of this. It is the diameter of that pitch circle divided by the number of teeth. This is the metric method of identifying gears, and you get millimeters per tooth. Imperial gears, or gears specified with the diametral pitch, need to run with other gears specified with the same diametral pitch. All right, so if you take two gears and one has a pitch of 20 and the other has a pitch of 24, they will not mesh together. So the pitch has to be the same, and the same holds true for the module. So the pitch on two gears on the module on two gears must be the same. So to get a sense of the sizings of these, you can refer to this image. So from this image you can see that small modules equate to small gear teeth. And that's the opposite true for imperial gears, because we're talking about the number of gear teeth you can find within an inch around that circle. So for a large module or a large diametral pitch, we see small gear teeth. And again, the pitch of two gears must be the same in order for them to mesh. So we may cut gears at different lengths. We can cut them at at stubs or at full depth, and we can cut them at different prescribed angles. So there's an excellent how it's made video that's posted. The link is again posted on Blackboard, and it'll describe the different methods of designing those gear teeth. And what you'll see is that it takes a very specific set of tools in order to do it. And in order to design a gear, you can, in theory, design a gear with any number of teeth at any pitch angle you desire. However, all the other gears, in order to mesh with it, must also have the same set. So that's why there's been developed standards of typical gear teeth sizes and pitch numbers and modules in order that those gear teeth can be interchangeable and mesh with one another. So the standard sizes, the standard pressure angles is 14 for really old gears, and you can usually see pressure angles of 20, 22.5, 25 degrees. So the last thing we need to discuss before looking at how forces are transmitted between gears is looking at what happens when our conjugate action is not true. That is interference. So interference means that the teeth will not mesh. And what we're going to look for is the smallest number of teeth on the gear to avoid that will keep you from having interference. So the smallest number of teeth on the gear will get you the smallest gear, and in general those tend to be cheaper gears. So our design preference is to look for the smallest one that will work for us. So we're looking for the smallest number of teeth on the pinion, that is the smaller gear, that will avoid interference. And we do this by equation. So for spur gears, the smallest number of teeth on a pinion equals this. So this equation says that the minimum number of teeth, the smallest number of teeth you'll get on a pinion, is based on 2k divided by 1 over 2 times r times the square sine of the pressure angle. So in this equation, k is equal to either 1 or 0.8. 1 if the teeth are full depth teeth, so these are fully cut teeth, or 0.8, we're just talking about stubbed teeth, which are smaller. The pressure angle, again, is that line of action between where the gears are attacking, and it's usually a standard of 20, 22.5, 25, something within that range. And the value r is the ratio between the size of the gear that we're trying to run and the size of the pinion. So to run one gear against another gear the exact same size would not do anything in terms of transmitting torque or power. You'd get the same power in, power out. But instead, the gear, and then that equation would be 1. So that would be the absolute smallest gear you could do at that particular pressure angle. So you can affect this equation by the ratio of the gear and the pinion that you want to use in order to get a particular ratio that you want, and as well as the pressure angle that you're going to select. So when this comes to gear design, we often have to just pick a pressure angle to begin with, and then change our choices later if that ends up affecting our decision. The same thing happens with the K. We can also look at, so this is for spur gears. Helical gears interact at a particular angle across their face as well. And so they have a slightly different minimum number of teeth. So for helical gears, the minimum number of teeth on the smaller gear, the pinion, is equal to, so this equation says that 2k, which k again is the full or stubbed teeth, multiplied times the cosine of the helical angle divided by 1 plus 2 times that ratio of the gear to the pinion times the sine of the tangential pressure angle is all multiplied times that ratio plus the square root of the ratio squared plus 1 plus that 2 times the ratio and the sine of that squared of that pressure angle, tangential pressure angle again. So the difference here is that we're going to be talking about a tangential pressure angle and a helical angle because these gear teeth interact at an angle to one another. So how this will work is we will specify, given a particular power change that we want to occur, a ratio that we need to achieve. We put this ratio in here, decide on a helical angle, or if we're talking about spur gears, just pressure angle, and a tangential pressure angle, again for the helical, and calculate the minimum number of teeth on the pinion. Then we're going to need to round up. Because this equation is going to give you a partial answer. If you get an answer like 16.35, obviously it doesn't make sense for a gear to have 0.35 teeth. So you need to round up to 17 gears in order to avoid interference. From that, and you know the gear ratio that you wanted, you can find out the number of teeth on the gear itself. From there, we can start working out what are the forces acting on that gear tooth. And that's what we're going to do next time. That'll about do it for this video. Until then.